Gravity has been a topic of scientific study for centuries. It is the force that keeps us grounded on Earth, causes objects to fall, and keeps planets in orbit around their stars. However, in recent years, a revolutionary discovery has changed the way physicists understand gravity. Did you even know that gravity is not a force at all? Greetings and welcome to my channel. Today, we're going to talk about the discovery that changed physics. Gravity is not a force. The discovery that gravity is not a force has profound implications for our understanding of the universe. It has led to discoveries in technologies and has fundamentally changed the way we think about the nature of gravity. Einstein's theory of general relativity is a testament to the power of human curiosity and the potential for scientific discovery to transform our understanding of the world around us. But first, if you haven't subscribed, please subscribe to my channel and enable the notification bell so you can see more interesting videos like this. So let's dive in and learn more about this fascinating development. Gravity is one of the maximum essential forces within the universe. It affects everything from the movement of planets to the simple act of standing on the ground. For centuries, physicists believed that gravity was a force that acted between masses. But a revolutionary discovery in the early 20th century changed everything. The general theory of relativity, developed by Albert Einstein in 1915, introduced a new understanding of gravity. Instead of viewing gravity as a force, Einstein saw it as a curvature of space and time caused by the presence of matter and energy. According to this theory, objects with mass do not directly attract each other, but instead, they cause a curvature in the fabric of space-time that results in the apparent force of gravity. This means that the force of gravity that we observe on Earth is the result of the planet's mass curving the space-time around it. Similarly, the Sun's mass curves the space-time around it, keeping the planets in their orbits. Even the presence of a massive object like a black hole creates a curvature in space-time that causes other objects to move in a certain way. The fashionable idea of relativity has been verified to be exceptionally correct in describing the conduct of gadgets within the cosmos. It has been used to explain phenomena such as the bending of light by gravity, the gravitational waves detected by LIGO, and the behavior of objects in strong gravitational fields. Newton's theory of gravity, also known as Newton's law of universal gravitation, states that the force of gravity between two objects is directly proportional to their mass and inversely proportional to the square of the distance between them. This law is still used today in many situations, such as calculating the force of gravity between planets and stars. Newton believed that the path that objects take would be the shortest to minimize energy use. This is known as the principle of least action, which states that nature always chooses the path that minimizes the action, a quantity related to the energy. However, this principle is not specific to gravity and applies to all physical systems. It is worth noting that while Newton's theory of gravity was extremely accurate for its time and is still used today in many situations, it was eventually superseded by Einstein's general theory of relativity, which provides a more complete and accurate description of gravity. In the general theory of relativity, gravity is not considered a force, but rather a curvature of space-time caused by the presence of mass and energy. Einstein's theory of general relativity challenged the idea that gravity is a force between two objects with mass. Instead, Einstein proposed that gravity is a curvature of space-time caused by the presence of mass and energy. In this theory, objects with mass do not directly attract each other, but instead, they cause a curvature in space-time that results in the apparent force of gravity. One consequence of this theory is the equivalent principle, which states that all objects fall on the equal price in a gravitational field, no matter their mass or composition. This has been confirmed by numerous experiments and observations, including the famous feather and hammer drop experiment conducted by astronaut David Scott on the Moon during the Apollo 15 mission. Einstein's theory of general relativity has been incredibly successful in explaining a wide range of gravitational phenomena, including the behavior of stars and galaxies, the bending of light by gravity, and the detection of gravitational waves. It has also led to new insights into the nature of space and time, as well as the origin and evolution of the universe. Einstein's theory of general relativity describes gravity as the curvature of space-time caused by the presence of mass and energy. In other words, mass and energy warp the fabric of space-time around them, creating a gravitational field that affects the motion of other objects. Imagine a rubber sheet stretched out flat, and you place a heavy ball on the sheet. The ball will create a depression in the sheet, causing nearby objects to roll toward it. This is a simple analogy, to understand the concept of space-time curvature. In reality, the curvature of space-time is more complex and cannot be visualized so simply, but the analogy helps to illustrate the basic idea. Similarly, when we have a massive object, like a planet or a star, it warps the space-time around it, creating a gravitational field. This gravitational field influences the motion of other objects that come close to it. For example, a planet orbits a star because the gravitational pull of the star warps the space-time around it, causing the planet to follow a curved path. The curvature of space-time also affects the behavior of light. Light follows a straight path through space, but when it passes through a region of space-time curvature, its path appears to be bent. This is known as gravitational lensing, and it has been observed by astronomers as evidence of the curvature of space-time. The gravitational pull of an object is indeed due to the curvature of space-time around it, and the closer an object is to the massive object, the stronger the gravitational pull becomes. Einstein's theory of general relativity describes gravity as the curvature of space-time caused by the presence of mass and energy. This means that the mass of an object warps the fabric of space-time around it, creating a curvature in space-time. The greater the mass, the greater the curvature. When another object is nearby, it follows a path through the curved space-time, and this path appears to be curved due to the influence of the massive object's gravitational field. This curved path is what we observe as the gravitational pull of the object. The nearer an item is to the huge item, the extra the curvature of space-time around it, and the more potent the gravitational pull becomes. For example, the Earth is attracted to the Sun because the Sun's massive gravitational field warps the space-time around it, causing the Earth to follow a curved path around the Sun. Similarly, the Moon is attracted to the Earth because the Earth's gravitational field warps the space-time around it, causing the Moon to follow a curved path around the Earth. This is also why objects in the universe are attracted to each other. Any two objects with mass will exert a gravitational pull on each other, which is proportional to their masses and the distance between them. The closer the objects are to each other, the stronger the gravitational pull becomes due to the increased curvature of space-time around them. The Earth's mass warps the space-time around it, creating a gravity well that attracts objects towards it. The greater the mass of the object, the deeper the gravity well, and the stronger the gravitational pull. The Moon also has mass, and it warps the space-time around it, creating its gravity well. However, the gravitational field between the Earth and the Moon is not strong enough to pull the Moon toward the Earth. Instead, the Moon orbits the Earth because it is in a state of continuous free fall towards the Earth, following a curved path around the Earth due to the curvature of space-time around it. This same concept applies to other objects in the universe as well. For example, the Sun's mass warps the space-time around it, creating a gravity well that attracts all the planets in our solar system towards it. The planets follow elliptical orbits around the Sun due to the curvature of space-time around it. Einstein's theory of general relativity has been used to explain the behavior of gravity wells around planets in our solar system, and it has also been used to develop space exploration technologies such as gravitational slingshots, which use the gravitational pull of other planets to accelerate spacecraft. In a gravitational slingshot, a spacecraft is directed toward a planet or other celestial body and uses its gravity to change the spacecraft's speed and direction. By carefully selecting the trajectory and speed of the spacecraft, engineers can use the gravity of the planet to increase the spacecraft's speed and conserve fuel. However, despite the success of Einstein's theory of general relativity, there are still many mysteries and unanswered questions in the field of physics, such as the nature of dark matter and dark energy, and the unification of gravity with the other fundamental forces of nature. It is possible that in the future, new scientific discoveries and breakthroughs will challenge or expand upon Einstein's theories, just as his theories challenged and expanded upon the earlier theories of Isaac Newton. But for now, Einstein's theory of general relativity remains a powerful and elegant explanation of the behavior of gravity and the curvature of spacetime. The theory of general relativity fundamentally changed our understanding of gravity. Prior to Einstein's discovery, physicists believed that gravity was a force that acted instantaneously across vast distances. Thank you for tuning into our video today. Don't forget to like, share, and subscribe to our channel for more exciting news and updates from the world of science and beyond. Let us know in the comment box what you think the future holds for the understanding of gravity. See you in the next video.